Imagine that you're walking along a crowded sidewalk. The easiest way to get through a crowd of people is to glide slowly through, finding a path without running into people. If you just take a running start and head straight for the crowd of people, you will quickly slam into someone and won't get very far. This is similar to what happens in a cornstarch and water mixture. The solid cornstarch acts like a crowd of people. Pressing slowly into the mixture allows the cornstarch to move out of the way, but tapping the mixture quickly doesn't allow the cornstarch particles to slide past each other and out of the way. This is an example of a non-Newtonian fluid. But what are they, and how do they work? A non-Newtonian fluid is a fluid that defies Newton's law of viscosity. Viscosity is the resistance to flow in a fluid. It's kind of like the friction between the molecules in the fluid. Newton described the flow behavior of fluids with a linear relationship between shear stress and shear rate, resulting in a proportionality constant, the viscosity of the fluid. Viscosity is the slope of the graph of shear rate versus shear stress. Shear stress is the component of stress or force vector parallel to the cross-section of the material. Shear rate is the rate of change in velocity at which one layer of fluid passes over an adjacent layer. For Newtonian fluids, a fluid's viscosity is only dependent on temperature. For example, honey flows more easily when you warm it up and becomes thicker when it gets cooler. A non-Newtonian fluid has the same dependence on temperature, but its viscosity can be changed by applying pressure or shear stress. Non-Newtonian fluids display a nonlinear relation between shear stress and shear rate, have a minimum yield stress, or viscosity that is dependent on time of applied stress. A constant coefficient of viscosity cannot be defined with non-Newtonian fluids. These fluids behave differently, displaying forms of liquids and solids under certain conditions, because of several factors related to the structural reorganization of the fluid molecules. These fluids are usually heterogeneous mixtures of suspensions or colloids. The classification of non-Newtonian fluids depends on how the fluid viscosity varies in response to the duration and magnitude of applied stress. The viscosity of thixotropic fluids decreases over time under stress. These include yogurt, some paint, and clay. The viscosity of rheopectic fluids increases over time under stress. These include printer ink and cream. The viscosity of Bingham plastics depends on a minimum stress before beginning to flow as a Newtonian fluid. These include clay suspensions, drilling mud, toothpaste, and mayonnaise. The viscosity of shear thinning or pseudoplastic fluids decreases with increased stress. They're not time dependent and include syrup, paint, blood, nail polish, ketchup, and quicksand. Ketchup will not flow until it's squeezed or shaken, and applying more stress to quicksand causes one to sink faster. The viscosity of shear thickening or dilatant fluids increases with increased stress. They're also not time dependent and include wet sand and the mixture of cornstarch and water. One of the most common examples of a dilatant is the mixture of cornstarch and water, or oobleck. As we can see, the fluid appears to be a liquid, but when stress is applied, the fluid rearranges to form a solid. With enough force, a ball can bounce off the fluid. With too little, it will sink. Many household items apply to non-Newtonian fluids, but there are many more possible applications. Shear thickening non-Newtonian fluids may be used in body armor. The fluid would provide flexibility for movement while providing rigidity to resist piercings by bullets and knives. However, against slow attacks such as slow but forceful stabs, the dilatant would not provide any additional protection. Shear thickening or rheopectic materials may also be used for shock absorbers and protective equipment to reduce impact stress in athletics, motorsports, and transportation accidents. Shear thinning materials are also useful for drilling fluids, and they save pumping power. Wrapping it all up, Newton's law of viscosity states that Newtonian fluids have a linear relationship between shear stress and shear rate, passing through the origin, resulting in a constant viscosity. Non-Newtonian fluids do not follow Newton's law of viscosity. Non-Newtonian fluids can be classified by being thixotropic, rheopectic, being in plastic, shear thinning, or shear thickening, depending on the duration and magnitude of applied stress.